In this video, I want to give you a reminder of some of the fundamentals of trigonometry, specifically for right triangles. When we look at right triangle trigonometry, we have a few extra tools that make getting information about triangles easier. So remember that a right triangle is a triangle that involves a 90-degree angles. Two of the sides of the triangle are perpendicular to one another. So, if you're measuring in radians, they have an angle of pi over 2 radians between. Okay. So with the right triangles, we have a couple of different mathematical entities that we can use to gain and transform information about these triangles. We have the Pythagorean theorem, and that gives us a relationship between the sides of the triangle. Right, so we know that if we draw in a right triangle here, if I call the legs of the triangle A and B and the hypotenuse C, we have the relationship that A squared plus B squared is equal to C squared. Okay, and in addition to that, we also have, when we're thinking about standard Euclidean geometry, we have the sides, or the angles. And we always know that when we have a triangle, a planar triangle, the sum of the angles is either 180 degrees or pi radians. Okay. So when you have a right triangle, that gives you a little bit of information, because one of your angles is 90 or pi by 2 radians, and the other two angles have to be complementary. Okay, so they have to add up to another 90 degrees. So if you think about, let's say we name the angles here. Let's call one of them theta. And if I call one of them theta, we have the right angle, which is 90 degrees, and the other angle must be 90 minus theta. So we can get the angles in terms of one unknown. If we know one of the angles that's not a right angle, we can determine the other angle using the sum of angles. Just like with the Pythagorean theorem, if we know any two sides of the triangle, two of the side lengths, we can deduce the third side length using the Pythagorean theorem. Okay? So we know that theta plus 90 minus theta plus 90, that's our right triangle. That adds up to 180 if we measure things in degrees, or alternately if we measure things in radians, theta plus, let's write this, theta degrees, how about that? And then we can write this as pi by 2 minus theta in radians plus pi by 2 is equal to pi radians. So we have two angles that are not the right angle, and those are complementary to one another, so that their sum is 90 degrees, or pi by 2 radians. So we have these relationships, and then we also can use the trigonometric functions to describe connections between the angles and the sides of right triangles directly. Right? So if you recall the definition of sine and cosine, those are coming from looking at a triangle constructed from the unit circle, so the hypotenuse was 1. But it turns out that if you scale the right triangle, if you make all of the sizes, or all the side lengths larger using the same multiple, then you can still use the trigonometric functions to link together ratios of the sides. Basically, we're thinking of similar triangles. So let's suppose that this is the unit circle right here, or I would draw in the unit circle. This is a triangle from the unit circle. Then the x component would be cosine of this angle right down here, cosine of theta, and this y component would be sine theta. And if I draw a bigger version of the same triangle, try to scale it properly here, the sides here, let's call this A, and I'll call this O. I'll explain why in a second. And I'm going to call this H. Let's Let's make these all capital letters. Okay. So now I've named the three sides of this triangle, and I'm thinking about, I want to construct this triangle with the same ratios of sides, so I want this angle to be the same as the angle of this version right here. Okay. Now, if we use similar triangle geometry, what we're thinking about is this being the same triangle, just enlarged, zoomed in or zoomed out. And this gives us other connections between the angles on the sides of right triangles. So we can say that the ratios of any two sides on this triangle would be equal to the ratio of the same sides on this triangle. So for example, we could say that sine of theta over 1, this vertical side divided by the hypotenuse, so sine of theta over 1 is going to be this side O divided by this side H, the opposite side from the angle divided by the hypotenuse. Okay, so that's O over H. We could do the same kind of thing with the cosine, right? So the cosine of theta divided by 1, think about the bottom side versus the hypotenuse, is going to be equal to the ratio A divided by H. The bottom side on top, the hypotenuse on the bottom. And then finally, we can do the same kinds of things with the derived trig functions if we want. I'll just do tangent as an example. So let's look at sine divided by cosine, the opposite side divided by the adjacent side. Sine over cosine is equal to tangent. So we can say that tangent of theta is going to be the same as O divided by A. So we can use the sine, the cosine, and the tangent to give us the connections between two sides, any pair of sides of this triangle, and one of the angles that's not the right angle. All right. So now we can use these relationships in combination to give us information about triangles, to connect one piece to another piece. So what I want to do is I'm going to show you some examples using the special triangles. Right? And then we'll see how how to explore this, how to connect these things together. So you've got Pythagorean theorem, which is a relationship just between sides. You have the sum of angles, which is a relationship between all the angles of the triangle. And then you have sine and cosine, sine, cosine, and tangent, really, which give you connections between two sides and an angle, okay, and a non-right angle. Okay, so let's look at, sometimes this is called solving a triangle. What I want to do is I want to start with a limited amount of information about the triangle. I don't want to know everything about it, but I want to use a combination of the Pythagorean theorem, the sum of angles, and the sine, the cosine, and the tangent to bring out all the features of the triangle that we might be interested in. So let's suppose, and we'll write a shorthand for the relationships between sine, cosine, and tangent using a mnemonic that you might have heard before. Sometimes people remember the relationships by making up a nonsense word of all those letters. So this is a pretty standard mnemonic in English schools. SOHCAHTOA tells us that the sine is equal to the opposite side divided by the hypotenuse. Ka, the next syllable there, tells us that cosine is the adjacent divided by the hypotenuse. And then finally, toa is tangent is the opposite over the adjacent. So that gives us kind of a very compressed way of remembering the connections between sine, cosine, and tangent and the ratios of the sides that they connect. Okay, so here's an example. Here's a triangle. And let's say that we know a little bit about this triangle. First, it's a right triangle, which will allow us to use these trigonometric functions automatically without any kind of extra baggage. And let's say that this side length, the vertical side length, is equal to 1. And let's make this angle 30 degrees or pi by 6 radians. So this is going to be one of the special triangles that we're familiar with. So there's partial information about the triangle. I'm telling you one side and one angle, and I'm telling you that there's a right angle in this. So from these two extra pieces of information, we're going to be able to figure out all the side lengths and all of the angles. Okay? So first, let's look at finding this other angle here. And for that, since I know two of the angles in this triangle, I can use the sum of angles to deduce what that last angle has to be. I need to have all three angles have to add up to 180 degrees or pi radians. So let's do it in degrees first and then in radians after that. So in degrees, we have a 30-degree angle, we have a 90-degree angle, which is the right angle, and then we have this other angle. So what does that have to be? We need 30 plus 90 plus this angle, maybe we call it phi, to be equal to 180 degrees. That's the sum of angles requirement. So if we go ahead and solve this equation for phi, we'll know all the angles of this triangle. So 30 plus 90 is 120. And that plus phi has to be 180 degrees. So if I subtract 120 from both sides, I find that phi should be 60 degrees. Okay? So this is a 30, 60, 90 triangle in radians. We can do the same kind of thing. This angle is pi over 6 radians. This angle, the right angle, is pi over 2 radians. And this unknown angle is phi, which the sum of all three of those must add up to pi radians. So let's go ahead, find a common denominator, and work out the details here. So we have pi by 6 plus pi by 2 is equal to, plus phi is equal to pi. So get a common denominator. I can multiply top and bottom of the second fraction by 3, and that'll give me a common denominator of 6. So I get 3 over 6 pi, the same as a half pi, so that's good. So adding these together, we get 4/6 pi, and if I introduce that same denominator of 6 over here, right, this is 6 pi over pi, that's equal to just 1 pi, so that's good. And subtract the 4/6 pi from both sides, and theta looks like 2/6 pi, which we can reduce that a little bit. We have a common factor of 2 in the numerator and denominator, so I can write that as pi over 3 radians. Okay, so we have pi over 6, and then in radians here, we would have pi over 3 radians. Right? And the 90-degree angle is pi over 2 radians. So 30, 60, 90 triangle, or pi over 6, pi over 3, pi over 2 triangle. Now let's figure out what all the other sides are. Since we don't have two sides, we cannot yet use the Pythagorean theorem to deduce the length of the third side. So we're going to need to use a trig function to get a connection between two of the sides, the one that we know and one of the sides that we don't know. Okay. So what I'd like to do is maybe we'll use this first angle that we were given, this 30-degree angle or pi over 6 radian angle, and we want to find, I'll use the same labels that I used before, the adjacent and hypotenuse. Let's call this guy A and this guy H. And you have a choice here on what trig function you want to use, depending on the order in which you compute these things. So, for example, let's suppose that we want to find H first. If we want to find H first, I need a trig function that connects this angle with the opposite side and the hypotenuse. Okay, so I want to connect the opposite side and the hypotenuse. So if I want to do that, the only trig function that connects those two sides is the sine function. So sine is opposite over hypotenuse. So we have sine of pi over 6 radians is equal to the opposite side, which is a 1, divided by the hypotenuse. Okay. So if I want to find the value or the size of h from this, then I'm going to go ahead and solve this equation algebraically. Get h by itself in the numerator on one side of the equation. So we find that h, I'll multiply both sides by h. Let's do this one step at a time. And that gives me h multiplied by sine pi over 6. That's equal to 1. And then I'm going to divide by the coefficient of h, which is the sine of pi over 6. So h is equal to 1 divided by sine of pi over 6. And I need to remember that sine of pi over 6. So if I want to do that, I can go back to that table of values of sines and cosine that I constructed before. Look at 0, pi by 6, and this is the only part of the table I really need to construct. I have cosine, and I have sine. I know that everything in my table gets divided by 2, and everything in my table gets a square root. And cosine starts at the value 1, so I started at cosine square root of 4, because square root of 4 is 2 divided by 2, which is 1. And then I count down for that. And sine starts at 0, and I count up from that. So it looks like the sine of pi over 6 radians is the square root of 1 over 2. The square root of 1 is 1. So I have 1/2 as the value of sine of pi over 6 radians. So we have h is 1 divided by 1/2. If you want to simplify that fraction, you can bring this 2 from the denominator of the denominator into the numerator. So this looks like 2 divided by 1, which is just 2. So the value of h, using this trig function, we find that it's equal to 2. The hypotenuse here is 2. Okay? Alright, so now we've got one last thing to figure out. We have this adjacent side to figure out. And now we have enough information where we really have a few different choices that we can make. We could use the Pythagorean theorem and the value of h, the hypotenuse, and this side to find the value of the adjacent side. Or we could use a different trig function. Since we know the hypotenuse and this adjacent side, we have a choice of the trig function that we would decide to use. We could use the cosine and we could use the tangent and use the opposite and adjacent side, or we could use the cosine and use the hypotenuse that we discovered and the adjacent side. What I'm going to do is I'm going to use the Pythagorean theorem just so that we get kind of a little bit of practice with all the different tools that we have at our disposal. So we know that h is equal to 2. We know that this leg of the triangle is length 1, and we want to find that adjacent side. So if we map those things into this kind of traditional statement of the Pythagorean theorem, we can see what the value of this adjacent side should be. So we have a squared, that's the adjacent side to our angle, and this lower leg, plus this vertical leg, which is b, so that's 1 squared. And their sum should be equal to the hypotenuse squared, which we called h, but we found the value of h to be equal to 2. So that should be 2 squared. Okay? So now that we've got this relationship, all we need to do is solve for the value of a. A squared is equal to a squared plus 1 is equal to 4. 2 squared is 4. Subtract 1 from both sides. A squared is equal to 3. And then square root both sides. A is equal to the square root of 3. And that finds the last piece of this triangle. So let's fill everything in. So this is a 30, 60, 90 triangle. We see that one of the legs has length 1. The other leg has length square root of 3. And the hypotenuse has length 2. Okay? So that's kind of a simple example of right triangular trigonometry using one of the special triangles and some of the special values of sine and cosine. Remember that when you're dealing with a right triangle, you have all of these tools at your disposal to help uncover the different pieces of the triangle. Okay? And if you have a hard time remembering how sine, cosine, and tangent connect to that right triangle, you can remember the mnemonic SOHCAHTOA. That tells you which trig functions are linked with which sides of the triangle in relation to the angle that you're using.